So today we're going to talk mathematically about equilibrium, and we're going to learn how to write the expressions and do some calculations for the equilibrium constant, which is known as Kc. So if we have a reaction where A plus B yields C and D, and the lowercase letters are their coefficients, our Kc expression is going to look like this. It's the concentration of C raised to its coefficient times D, so the products raised to their coefficients, over A and B raised to their coefficients. And remember, those square brackets mean concentration or molarity, moles per cubic decimeter. So we're going to talk about gases a lot. We're going to talk about aqueous solutions a lot. So Kc has a fixed value for a given reaction at a specific temperature. The only thing that'll change Kc is a change in temperature. We'll get there later on. But just know that changes in pressures, initial amounts of reactants and products, catalyst, all those sorts of things, they don't change Kc. And we're going to see that numerical values for this equilibrium constant will only come from experimentation. We can't predict it from the balanced equation or something like that. So here's your science/math joke, since we're going to be dealing with fractions. All right, first thing we're going to do, we're just going to write these expressions. No numbers involved yet. So we have nitrogen, oxygen forming nitrogen monoxide. Kc is going to equal the concentration of the products over the reactants, and we're going to turn those coefficients into exponents. So it's going to be NO squared divided by the product of nitrogen and oxygen. Most of these had coefficients of 1, so exponents of 1. All right, the next one, methane and chlorine yields chloromethane and HCl. So try and write that. Check your work. Okay, and do this third one all on your own, and then you can play the video some more. So I'll go ahead and issue a word of caution that you're going to use parentheses and exponents very, very carefully in your calculator when you do this. Okay, so I already mentioned that concentrations, we're talking about aqueous solutions and gases. Well, what happens if we have a pure liquid or pure solid? Where the activity or the concentration is going to be taken as 1. Okay, so that's kind of the short story of all this. If you go on to HL, more of this will make sense later on. So let's try this. Write equilibrium constant expressions for the following reactions. I've got water forming hydrogen ions and hydroxide ions. So I'd write my Kc expression like so, except that this is liquid water. Well, liquid water is going to have a concentration of 1. So I put a 1 in the denominator. And dividing anything by 1 becomes just the numerator. Okay. Here's one, calcium hydroxide and hydrochloric acid reacting to form water and calcium chloride. So I write my Kc expression as normal. But again, we have liquid water. So I can cancel that out and make that a 1. And if you had a solid, you'd do the same thing. So for right now, that's just kind of an FYI, but now you know. Let's move on to actually calculating it. So nitrogen and hydrogen are placed in an empty 5-liter container at 500 degrees Celsius. When equilibrium is established, 3.01 moles of nitrogen, 2.1 moles of hydrogen, and 0.565 moles of ammonia are present. Calculate Kc for the following reaction at 500 degrees Celsius. Okay. So our Kc expression is going to be like this. Now, remember that these brackets mean concentration. They mean molarity, or moles per cubic decimeter, moles per liter. And I have moles, and all of these are in a 5-liter container. So I can't just divide by 5 at the end. I'm going to actually have to put these in. So I'm going to put in my values, but I'm going to divide each one of my moles by 5. Again, parentheses, things like that are your friends. Try and type this in your calculator. Like, seriously, try it. Pause the video, try it. Make sure you can work your calculator correctly, and make sure you get that answer. Let's try another one. This is a little bit different, but same idea. Okay. We put 10 moles of dinitrogen monoxide into a 2-liter container at some temperature, where it decomposes according to that equation. At equilibrium, 2.2 moles of dinitrogen monoxide remain. Calculate the value of Kc for the reaction. Okay. So we know that we started with 10 and we ended with 2.2 moles of our reactant. So that means 7.8 moles reacted. Okay. Well, 7.8 moles of that turned into some nitrogen and some oxygen. It decomposed. It didn't turn. We're not doing alchemy or anything. Well, we need to know how many moles of nitrogen and how many moles of oxygen we produced. So we're going to turn to our friend stoichiometry and do that. So I had 7.8 moles of N2O. I'm going to find out how much nitrogen we produced. Our mole ratio is 2 to 2. So we produced 7.8 moles of nitrogen. Now, we are wanting to know concentrations, so I'm going to go ahead and divide by my 2 liters to get the concentration of nitrogen. And then we're going to do a similar process to find the moles of oxygen and then the concentration of oxygen. So I still start with my 7.8 moles of N2O. My mole ratio is 1 over 2. So that gives me 3.9 moles of oxygen. I'm going to divide that by 2 liters to get a concentration of 1.95. So I know the concentrations of my products. And I know how many moles of N2O were formed, which we can turn that into a concentration by dividing by 2 liters. Okay, so now we have all our concentrations. So we can write our Kc expression. Oh, there should be a square right there. Go ahead and add in a square. And square this guy. Which means that's not the answer you should get. Let me grab my calculator and fix my work. You should get 0.0408. All right, not this, 0.0408. Here's another one. We're doing some algebra, honestly. An equilibrium mixture in a 1-liter container has 0.25 moles of PCl5 and 0.16 moles PCl3. What is the equilibrium concentration of chlorine? Okay, so we're already at equilibrium, and yay, we're in a 1-liter container. So 0.25 moles divided by 1 liter is 0.25 molar and 0.16 molar. So I'm going to write the Kc expression, and we know that that's equal to 1.9. We also know 2 of our 3 concentrations. So here we're just going to flex our math muscles a little bit and solve for chlorine. And our chlorine concentration comes out to be 1.216 molar, or moles per cubic decimeter. Okay, so what do all these numbers mean? Well, if the reaction is product favored, meaning there's generally higher concentrations or more product than reactant, we're going to see that that Kc value is greater than 1. Think about it. If the products are in the numerator and there's more of the product than there is reactant that's in the denominator, we'll have like a top-heavy fraction. It'll be greater than 1. If it's reactant favored, if there's more of our numerator reactants than there are, our denominator reactant than our numerator product, we're going to have a value much less than 1, or less than 1. And so if it's really small, we know that that reaction really doesn't proceed forward. If Kc is rather large, then we know that this reaction goes almost to completion. So here's your mastery check. You'll fill this out in Google Forms, and we'll go from there.